Okay, welcome back to Math 103, College Algebra. This is section 4. We look at types of functions, rate of change, primarily having to do with linear type functions. A linear function is represented by f of x equals mx plus b, where m is the slope, b is the y-intercept. Personally, I prefer calling them rate of change and initial value. And again, I apologize for my horrible writing. Okay. You can represent data using a table, scatter plot, linear function. Let's suppose that a car is initially located 30 miles north of the Texas border, is traveling north on Interstate 35 at 60 miles per hour. If I want to create a table showing the distance from the border as a function of hours, okay, let's use x for time, y for distance. When we start tracking the time, when x is 0, the car is 30 miles north of the border. 1 hour later, it's at 30 plus 60, or at 90 miles away from the border, because it's traveling at 60 miles each hour. After 2 hours, it's 150 miles from the border. And after 3 hours, it's 180 miles from the border. And I could keep going with my table here. Okay. If I'm going to draw a scatter plot, we've got 0, 1, 2, 3, 4 hours. Okay, we'll go with 30. So that's 30, 60. Whoops, I don't want 60. Yeah, each line is 30, so that's 30, 60, 90, 120, 150, okay, 180. To 10. I got to fix my numbers over here. I apologize. So we said that this is going to be 90 plus 60 is 150, 210, 270, and so on. So after 0 hours, we're 30 miles from the border. 1 hour, we're another 60, so we're 90 miles. After 2 hours, we're another 60, so we're 150 miles from the border. And after 3 hours, we're 210. So there's a scatter plot. I could draw a line on there because time is continuous and we are going to hit every point in between, but the blue dots are technically the scatter plot. Okay. We could represent this data with a linear function. Y equals mx plus b. Remember that b is the initial value and that we're initially 30 miles from the border. We're traveling at 60 miles for each hour, where x is the number of hours. So y equals 60x plus 30, or f of x equals 60x plus 30. The initial value is 30. We go 60 miles each hour. Now you'll notice that when I drew this line, I started here at the 0, 30, and went to the right and up. I didn't go down the opposite direction because we started there. That's our initial value. So typically with a line, the domain can be all real numbers, but in this case, the x value has got to be greater than or equal to 0. Also, my y value, the minimum y value is 30, and then they go up from there. So my range is y is greater than or equal to 30. In the future, we'll get a lot more in depth into domain and range, a little bit more understanding of them, as well as formal way to write domain and range. But at this point, this early in the course, the domain is x values greater than or equal to 0. The range is y values greater than or equal to 30 is sufficient. Similar problem. You currently have $100 in a savings account. Each week when you get paid, you add $50 to the account. So my table, where x is the number of weeks, y is the amount of money. After 0 weeks, or initially, I have $100 in my account, or you have $100 in your account. The first week, you add $50. The second week, you add another $50. The third week, you add another $50, and so on and so on. So you have a scatter plot. Or you have a table. I'm sorry, there's your table. Your scatter plot at 0, 1, 2, 3, 4. We could keep going because I don't know for how many weeks I'm going to do this. And let's let each line here represent $50. So there's 100, 200, 300, and so on. So you initially have $100, and then you add 50, and another 50, and another 50, and another 50. Now this one I don't want to draw a line because I don't have all of the connecting X points in there. I only have 0, 100, 1, 150, 2, 200, 3, 250, and 4, 300. They keep going, but we don't connect them. The linear function, we're adding $50 each week after starting with 100. Personally, I like writing this y equals 100 plus 50x, right? I start with 100 and I add $50 each week. To me, that makes more sense. And in some applications, it's fine to write the equation that way. Formally, y equals mx plus b. Y equals, or f of x equals 50x plus 100. The domain, again, x has got to be greater than or equal to 0 because we're starting at 0 weeks. Working forward from there, the range, you started with $100 and your amount in your account goes up from there. Very quickly, a constant function is a function that's constant. It doesn't change. There is no slope. There is no rate of change. F of x equals b. F of x equals 6. Y equals 10. Suppose I have $100 in my account and I never add to it. The value of my account is $100. If I graph a constant function, it's always going to look like a horizontal line. Slope, as I mentioned to you before, is rate of change. We find that rate of change by looking at the change in the y value divided by the change in the x value. We find the change in y by subtracting the y values and the change in x by subtracting the x values. So let's suppose we have 2 points. Let's say we have 310 and 720. That slope is going to be the change in y, or the difference in the y values, 20 minus 10, divided by the change in the x values, which is the difference in the x values, 7 minus 3. 20 minus 10 is 10. 7 minus 3 is 4. Now that fraction, 10 over 4, can reduce to 5 halves. We would have a slope of 5 halves. Okay. Suppose we have 512 and 810. I wrote 18. Let's make that an 810. Our slope, our rate of change, is the difference in the y values. I'm going to do 10 minus 12 divided by 8 minus 5. 10 minus 12 is a negative 2. 8 minus 5 is 3. Our slope, our rate of change, is negative 2/3. When our slope is positive, it means that the line is increasing. When the slope is negative, it means that the line is decreasing. The zero of a function is the value of x that makes a function equal to 0. Suppose I have f of x equals 3x minus 6. What value of x will make that equation equal to 0? 3x minus 6 equals 0. Okay, I set the 3x minus 6 equal to the 0, and I'm solving for x. Added the 6 to both sides, divide both sides by 3, x equals 2. X equals 2 is a 0 of the function because f of 2, which is 3 times 2 minus 6, equals 6 minus 6 equals 0. So 0 is the result of putting 2 in for x. 2 is a 0 of that function. A quick recap of graphing lines. I have a y value of 3, right? Remember, our b value is 3. If our b value is 3, we have a y-intercept of 0, 3. I am very picky about the fact that b is 3. The initial value is 3. Sorry, I keep jumping around here. B is 3. The initial value is 3, but that means that the y-intercept is the 0.03. The y-intercept is the point where the line crosses the y-axis. It's a 0.03. Now I have a slope of 2, 2 over 1. I go up 2 and over 1. That's the 0.15. I go up 2 over 1 again, and that's the 0.27. I connect those points, and I have my line. Let's do another one. 2/3 y equals, or f of x equals 2/3 x minus 5. Here's another alternative to just picking the points, right? We're putting the y-intercept and then plotting points from the slope. If x is 0, y is going to be 2/3 times 0, which is, put 0 in for x, 2/3 times 0 is 0, minus the 5 is -5. So that gives me the 0.0, -5. There's my, sorry about that, there's my y-intercept 0, -5. I'm going to pick another value for x. I could just go up 2 and over 3. Sometimes I have a hard time, quite honestly, determining exactly what point is that. So what I might do is say, what's another good value to substitute in for x? I'm going to choose 3. And the reason I'm going to choose 3 is I have 2/3 x times 2/3 times x. If I put a 3, the 3 divided by 3, those cancel, and I have 2 minus 5 is -3. That tells me that this point is 3, -3. And there's my line. We're going to spend in this course a significant amount of time initially with linear functions, but there are functions that are nonlinear function. A nonlinear function simply means any function that's not linear. We're going to talk about quadratic functions that look like y equals x squared. Notice that that's curved. It's not linear. It does not have a constant rate of change. It is nonlinear. We're going to look at square root functions, which look like this. Again, y equals the square root of x. That's curves. It's not linear. There's not a constant rate of change. We have the cubic function, y equals x cubed. Again, it's curved. It's not linear. Now, the absolute value function is going to look like a V, where this side is linear and this side is linear, so it appears linear-ish, but notice that there is that change. Here the function is decreasing, and then here the function is increasing. That's technically not a linear function. Speaking of increasing and decreasing, very formal definition here of increase and decrease. A function is increasing when, if x1 is less than x2, f of x1 is less than f of x2. x1 is less than x2 means f1 is greater than f of x2. Let me make that a little bit more clear. A function is decreasing when, as you read from left to right, the y values decrease. Notice as we go from left to right, the y values are decreasing. On the absolute value function, as we go from left to right, the function is decreasing. On the quadratic function, once we get down to this vertex, once we get down to this bottom point, notice now the function is going back up. So on this interval, the function is increasing. Absolute value function on this interval is now increasing. And the reason I only looked at the quadratic and absolute value is because notice the square root function is only ever increasing. There is no point where it's going downward. The cubic function is the same thing. As we read from left to right, it's always going up. Okay, So you look at the direction the function is moving as you read from left to right to determine increase and decrease. A little bit more on average rate of change. Remember what we said rate of change is? Rate of change, or specifically the average rate of change, is slope. Here's the slope formula, the average rate of change, y2 minus y1 over x2 minus x1. Now we said f of x equals 2x squared. This is not a linear function. It is quadratic. So that function, if I were to graph it, would look something like this. But if I go from this point to this point, what is the average rate of change? It's a very messy picture. Let me see if I can clean that up. A quadratic function that's curved, so I'm going to go from this point to this point. The average rate of change is linear going through those 2 points. F of 1 is 2 times 1 squared, or 2. F of 3 is 2 times 3 squared, which is 18. Remember, 3 squared is 9 times 2 is 18. So our average rate of change, or our slope, is the difference in the y values divided by the difference in the x values. Okay. 18 minus 2 is 16. 3 minus 1 is 2, so that would be 16 divided by 2, or 8. Our slope is 8. Our average rate of change is 8. Let's look at this example. U.S. population. We see the U.S. population in various years. 1800, U.S. population was 5 million people. By 1940, the population was 132. If I want to find the average rate of change from 1840 to 1900, the average rate of change is going to be y2 minus y1, 76 minus 17 divided by x2 minus x1, 1900 minus 1840. From 1900 to 1840, from 1840 to 1900 is 60 years. Over that 60-year period, what was the increase in the U.S. population? Well, 76 minus 17 is 59. So the United States population increased 59 million people over 60 years. That's just shy of 1 million people a year. It's actually 0.98 million people, which is 980,000 people per year. The United States population increased approximately 980,000 people per year. Use a little different color here to notice, to make a distinction from 1800 to 1940. From 1800 to 1940, what was the change in U.S. population? Well, notice that the population went from 5 million to 132 million. 132 minus 5 is 127. The United States population increased 127 million people in that time period. From 1800 to 1940 is 140 years. So in the 140 years from 1800 to 1940, the U.S. population increased 127 million people. 127 divided by 140 is 0.907. So that's about 907,000 people per year. So overall, from 1800 to 1940, the U.S. population was increasing at just over 900,000 people per year. But in this 60-year period from 1840 to 1900, it was even faster, closer to 1 million people per year. So there's an application of average rate of change. Okay, I hope that this video was helpful, and I hope to see you back next time when we talk more about linear functions.